This expression represents the core target of volume A. We are looking to prove the exact topological entropy, H, for a specific Collatz symbolic-branch itinerary, the sequence 1, 1, 1, 0. The standard approach to this calculation relies on combinatorics, specifically bounding the number of distinct Hofbauer domains. This requires tracking every individual interval at every depth n to find the growth rate. This line graph shows the empirical data for that domain count. To a depth of n equals 199, the observation is a perfect match for a linear complexity law. The number of domains, m sub n, is exactly 2n plus 1. However, while the data is exact for the first 200 depths, this linear law remains an unproven hypothesis. Without a rigorous proof for the domain count at every possible depth, the combinatorial route to an entropy value is incomplete. This reliance on m sub n restricts the proof to the limits of finite testing. To determine the behavior of the system as n reaches infinity, we must look beyond discrete counting and employ a different mathematical framework. This visualization represents the shift into functional analysis. We are tracking the continuous evolution of mass through the system. This is the age-structured transfer operator, denoted as T. Instead of tracking the boundaries of individual domains, it calculates the distribution of density across the system's branches over time. The operator advances in-flight seeds through the state space, resolving their trajectories based on the exact threshold bounds of the core mechanics. Under this framework, proving the exact entropy becomes a matter of mapping the spectral geometry of T. We begin by defining the system's core forward invariant interval, the core x, which occupies the segment from 0 to 1/2. We map the first step of the system's 5 branches. Pieces 0 and 3 are exact mappings onto the core x. Piece 1 maps onto the subinterval from 0 to 1/4. Piece 2 lands between 0 and 3/8, and Piece 4 maps to a narrower subinterval from 0 to 1/16. These 5 specific branch seeds define our initial counting measure, mu full. The 2 core mappings give us a weight of 2 for the core interval, with the remaining seeds added as Dirac measures on their respective bounds. This initial measure encapsulates the entire first step of the system's tautological complexity, providing the foundation for the operator's iteration. This is the spectral duality identity. It states that the total full system cylinder count, the value we need for entropy, is exactly equal to the inner product of the constant 1 and the transfer operator iterated n times on our initial measure. By framing the cylinder count as an operator iterate, the problem of combinatorial complexity is now governed by the rules of functional analysis. We can now apply the age-structured Perron theorem to evaluate the spectral properties of the operator. On the spectral plane, the operator possesses a unique peripheral eigenvalue, lambda, at 27/16. It is separated from all other eigenvalues by a distinct spectral gap, represented by this radius. This gap allows us to decompose the operator iterate into 2 components, a dominant rank 1 projection based on lambda and an exponentially decaying remainder, r. As n approaches infinity, the influence of the remainder vanishes, and the system's growth simplifies to the scaling behavior of the dominant eigenvalue. To prove the lower bound, we substitute that Perron decomposition back into the spectral duality equation. This expands the cylinder count into a bracketed coefficient evaluated by the left eigenfunctional, psi 0. We only need to consider the term psi 0 evaluated at the core, x. The renewal identity confirms this term rigorously equals exactly 1. Because the functional phi 0 is positive, the first term alone ensures the entire bracketed coefficient is at least 2. The exact values of the other 3 seeds do not impact the lower bound. Establishing this strict positivity proves that the exponential growth cannot vanish. We have secured a rigorous lower bound of c times lambda to the n. Combining this lower bound with the upper bound established by the operator norm, we take the n-through limit as n goes to infinity. The limit converges exactly to 27/16. We have a definitive proof that the topological entropy is h equals the natural log of 27/16. Now we can revisit the linear complexity law from the start of the video, the observation that there were 2n plus 1 domains. Because the operator t provided the growth rate directly, the combinatorial count was never actually a requirement for the proof. The linear law has been demoted from a load-bearing prerequisite to an independent structural problem. The proof succeeds by bypassing the discrete complexity counts entirely, finding the system's growth rate within the continuous spectral domain.